recording has started. To have Filip Ilievski come and give a talk. Filip graduated in the Netherlands, and he's been a postdoc at the Free University in Amsterdam. And he also worked with Ed Hovey. And he's going to talk to us about the identity of long-tail entities in text. So, Filip, thank you.
Great. Thanks a lot. Okay, thank you guys for being here. It's a big pleasure for me to be at ISI today. Indeed, I'm a postdoc at the Free University in Amsterdam. And, well, I would like to use this opportunity to tell you about the research that I did over the past years, mostly during my PhD, on the identity of long-tail entities in text. And I would like to take this knowledge perspective on this problem, I think it's an interesting topic that probably relates to other disciplines other than information extraction itself, because I think challenges that we experience with this could be found in other sub-disciplines in AI. And I think a knowledge-based vision might be also something that's interesting for other disciplines. So I hope it will be interesting for people that not only work in information extraction, but also a broader community. This talk will have two parts. In the first part of the talk, first half of the talk, I will talk about what I call the long-tail entities crisis. So I think we have computational systems that underperform on these long-tail entities. So within this part, I will define the long-tail entities as opposed to head entities. I will discuss what is the real system performance on both of these cases, and how does this relate to evaluation, and what is the influence of the way we evaluate things on the long-tail entities performance. In the second part, I will talk about my vision on how we can actually address this through use of deep and more systematic knowledge. I'll talk about the idea of hunger for knowledge in our systems. I'll talk about how we can read active reading machines. I'll go into these things in more depth later. And I'll describe a first preliminary work on these active reading machines on what we call profiling. And that's the work with Ed Hovey. Okay, so in the first part, I would like to tell you a bit about the problem setting here. So just to be sure, I'll use one slide to describe the task that we deal with. So the task of, when we talk about identity of entities in text, what we typically talk about in practice traditionally is the task of entity linking. The task of entity linking does this interpretation, has this interpretation relation of surface forms that we find in text that refer to entities, and now we want to essentially interpret them by making a link to an existing instance in some knowledge base. So if we have the text here, and if we, for example, want to establish the identity of the form Washington, we want to decide that within this context, the form Washington refers to the NFL team, and it does not refer to the city or the state or the government. And then if we're right, we get a reward and so on. Okay, so how far have we gone with this task? Well, if we look into one of the, let's say, some of the more recent papers on entity linking, we see very high performances. So you can see that this is a paper from 2016. I took it as an example, nothing particular, but just to show you the magnitude of these scores that are being reported. So you can see that these scores are very high. They're in the range of, let's say, 80s or 90s very often, which gives us an impression that we actually know how to deal with entities in text. So if you just see this table, we think, okay, 90% seems quite all right. Well, what I would like to argue here is that our systems might not be performing as well as we think that they do.
So in this table and in general in this talk, are you talking about just nominal linking, or are you going to
Right. So I will be talking mostly about. You're right that in some of these datasets there is disagreement on whether we're linking proper nouns or whether we are linking pronouns or nouns. I will take these datasets as they come, essentially. So I think in it's what is very typical is that we typically, I think in all datasets we always link proper nouns, and I think I will mostly be covering those cases. But there are datasets, and well, I don't think I'm covering those specifically, but there are datasets that also evaluate on nouns, let's say.
Okay, just proper nouns.
Proper nouns, yeah, that's the focus, yeah. Okay, okay, so there are cases when we run these systems and we get very weird interpretations back. So this is an example document where we have a murder described which happened in New Mexico, and if we run one of the state-of-the-art systems, which is Babelfy, it tells us that, well, in this murder we have the murderer is essentially an American president who is also a sprinter, and that person essentially killed a house. So we get this kind of interpretations, and I don't think it's necessarily a bad thing that we have systems that make mistakes. But what this shows is that these mistakes are very hard often to justify from a human perspective. So if we think about various notions of coherence, it's very hard to justify why would a president now kill someone in New Mexico, and that kill thing is not even a person. Okay, so how can we? Okay, so that's roughly the intuition where I'm intending to go with these long tail entities. But how can we actually quantitatively now describe these two groups, and can we then use that to measure performance on these two subsets? So what we can basically what I'm proposing is to divide all entities into head and long tail entities. When we talk about head entities, these are entities such as the French capital Paris, for which we have a lot of information in a background knowledge base. We find them very often in corpora, in communication, and we essentially need very little context to disambiguate this one. So if we have Paris, and if we have very little, if we want to refer to the French capital, we probably don't need to explain a lot what do we actually mean. If we have, on the other hand, a form like Paris referring to Paris, Texas, or a form Paris referring to something that is not in a knowledge base, then in these cases, we deal with long-tail entities. And these long-tail entities are extremely infrequent in communication, or at least quite infrequent. We have little to no knowledge about them in background knowledge bases, and we need a lot of context in order to actually deal with this. So for the purpose of this talk, I'm abstracting here within the long-tail entities between the two groups of entities that have very little knowledge and entities that have no representation at all. But I think for the purpose of this talk, actually, that this distinction is not necessarily relevant. So I will be talking about these two groups of head and long-tail entities. Okay, so given this table and this distinction between the two, can we actually somehow transform these descriptions into something that we can measure? Well, we can look into properties that we can fairly easily measure from the data, and I think that and these are very informative for us to capture the distinction. So we can look into ambiguity of surface forms, which is the number of instances that a certain surface form refers to. And in this case, I will talk about observed ambiguity. So it's the ambiguity that we measure on a corpus. So I use the corpora as proxy. Then I will talk about variance of instances. So the number of different forms that a certain instance is referred to. So if we have the US government, we sometimes find it being called Washington, and sometimes it's the US federal government, and so on. Next, we have the frequency of these forms and instances. So given the previous slide, I claim that the frequency also plays a role here. And then the popularity of instances, which we measure through a page rank in a knowledge graph. So essentially all of these properties, apart from the popularity, will be measured through the corpora as a proxy. And the page rank is based on the page rank in the knowledge graph of DBpedia here. Okay, so this is the analysis that we did. If we take these three systems that are, let's say, fairly recent systems, and we run them on all data, and then we we evaluate them on the overall data, and then we compare that to their performance on the subset of ambiguous forms only. We can see that consistently for all these three systems, we see that ambiguity plays a role. So given the ambiguity in the corpus, these systems perform worse on this subset. If we now couple the ambiguity with the frequency, what we would expect is that, given again the table that I presented earlier, we would expect that systems can deal much better with forms that are very frequent and that are not ambiguous. So that would be the bottom left corner in all of these heat maps. And we expect that basically having lower frequency and higher ambiguity, which is the top right corner, results in lower scores. So this is what we observe in this picture to quite a big extent. So you can see that for all three systems, the bottom left corner has very bright colors, showing that the performance here is very close to perfect. So it's somewhere between 70 and 100. Whereas in the top right, the colors are much darker. So you can see here that when we deal with ambiguous forms, when we deal with forms that are not very frequent, our performance goes very much down. Okay, so given these observations, if we now take only the ambiguous forms, can we say something about the skewness of the frequency skewness within these ambiguous forms? What I'm trying to present on this slide is essentially the distinction between having a form that has very high entropy, meaning that it refers, let's say, half of the time to one instance and the other half of the time to another instance. So that would be forms with high entropy here on the. Sorry, this doesn't work on the basically around on the right side, and on the other hand, we have low entropy cases where we have a very high frequency imbalance. So we have a form that is ambiguous, but in 99% of the cases it refers to one thing and then only occasionally to something else. What this plot shows is that for these ambiguous forms, we get we have consistent trend for all systems to have high performance when we have very high imbalance. So when we have very high skewness towards the popular class or the frequent class. And this performance goes very much down as we go towards cases which are which have this balanced distribution. Yes.
So this covers all of the entities, right? Correct.
So this covers the ambiguous
forms.
forms.
The entities by entropy, right?
So this covers the ambiguous forms only.
Okay.
The ambiguous subset.
It's just kind of striking that the most frequent baseline performance.
Right. So I was about to get to that, and actually, thanks a lot for pointing that. So indeed, the most frequent baseline here, it's computed on the corpus itself. So if we take the corpus and we get only the most frequent baseline, then we get this performance. Then you can see that for the 0.1 entropy bucket, so there we can see that the most frequent baseline has this performance of close to 100, and then as we go down, the most frequent baseline goes towards 50 or something.
Are you saying it's an ortho?
So what I'm saying here, what I'm trying to suggest here, and I'll go to a proof in the next slide, is that the systems to a large extent actually mimic the most frequent class, at least on average, and this is, I think, what we see here. So basically the systems have this skewness towards the most frequent class, and this is on average. So I don't. Sorry.
Okay, but I just want to make sure you said something about how it's the most frequent of the corpus. Is that to say that of the test corpus?
Right. So in the case of entity linking, we deal with the test corpus indeed.
So you couldn't actually get this performance.
No, you're right. So yeah, so sorry. Yeah, so you're right. So the baseline is maybe the word baseline is misleading here, but indeed it means if we take the corpus, we compute the most frequent instance for each of these forms on that corpus. So it's a cheating. I don't think you could get this baseline as a real world. But thanks for right. So okay, so what this suggests indeed is that the systems have this skewness towards the most frequent class, and we can also actually measure that. So if we take all the forms in our corpus, and if we rank their instances based on frequency or based on popularity. So the top three graphs here show have the ranks based on frequency, and the bottom three have the instances ranked based on popularity. You can see that the most frequent instance, again measured on the corpus itself, has much higher performance than all of the others. So this shows certain behavioral pattern in systems to follow frequency or popularity. So, and essentially popularity being such a strong estimate is not that strange, because actually in many systems that have been proposed after feature ablation, it has been shown that actually PageRank contributes quite a lot to the performance. So this is not necessarily extremely surprising, but it's kind of bad news. Okay. So the conclusion from all of these set of analysis is that we have systems whose performance declines when we move from the head to the tail of the entity distribution. And in addition, we don't see this in the 0.9 or the very high F1 scores that we get from systems. Okay, so I'll spend a few slides on why don't we actually see this. So I'll discuss the way we evaluate entity linking currently in our field. So this is a graph where we show the PageRank in a number of entity linking datasets. So essentially, the datasets here. So from the second one onwards, these are the PageRank, the box plots of the PageRanks of evaluation datasets in entity linking, in comparison to the first one, which is the PageRank in DBpedia. So you can see that there is a difference in orders of magnitude when it comes to the PageRank of the datasets that we evaluate, showing that we are actually evaluating on this head, on the frequent head to a large extent. And this is not strange. So we know that people have this reporting bias when we write documents. So it's not necessarily. I'm not blaming the data creators for this, but it's something to be aware of, that we have this frequency bias in the data that we deal with. And in addition, we measured so in addition, we created certain metrics to measure the extent of ambiguity, variance, dominance, entropy for entity linking and for a number of other tasks. And okay, this results here. So I'll not go in depth, but I'll basically just say that what we essentially measured is we measured low ambiguity on average, low variance, high dominance of the most frequent class, and the entropy measures have been also very low. So okay, so what this tells us is that what we are also evaluating on captures a lot from this head and captures very little from the tail. And as I've showed earlier, this has consequences for the systems that we built. Partially because if we use this as to some extent as training data, then we are essentially overfitting. But on top of that, essentially because there is no incentive for systems to actually deal with the tail if so little from the evaluation actually captures the tail. What can we do when it comes to evaluation in order to focus on the tail a bit more? So one thing that we can do is we can create datasets that deliberately addresses difficult cases. So what we did last year, and John May, I know, was organizing the semi-val competition last year at 2018. So we had this task where we created datasets where we ask systems to count event and participants within highly confusing, ambiguous data with a very long tail. So these were all entities that are not represented in common knowledge sources, and these were events that were local events. So these were local gun violence incidents to a large extent, and also some other incident reports from other domains. Okay, so that's one thing that we can do. What we can also do is either when we release data, or at least retrospectively after it has been released for the ones back, to have some information on how far can we go with simple baselines. So if we have another data set and we have PageRank performance being 70-80%, then maybe we should do something about it. I don't know, before we actually release it. And compute statistics on the head and the tail to know the distribution of the data. So I think that's important. And finally, I think it's important to experiment a bit with the metrics. So I think we could look into metrics that alleviate the frequency skewness. So we can use macro F1 score, for example, or evaluate separately on different classes of cases to show whether we are not only improving overall, but we are also improving specifically on cases that are known to be more challenging. Okay, so this concludes my first half of the presentation. Yes.
So, in your distinction between head and tail, if I look at a real corpus, so for instance, in our human trafficking project, we had sex ads from a large number of websites, and the head was on Backpage, which was the major vendor. And the issue is how much weight is in the long tail? So if the head covers 95% of the text that I see, then why bother with the long tail? Whereas if the head really only covers a much smaller percentage, then the tail is important to have a sense of, I have an entity linking system and I put it on the sex ads, it will do very badly because most of it is tail. Even though if I put it on Backpage, it does really well, but only on one side.
Right. So I think that statistically the tail should be statistically the tail is well, yeah, it very often covers a smaller proportion of the cases. That's indeed what we always see. I do think that that if we have, let's say, a corpus that is overall a long tail, then I think it perhaps it makes sense to rethink what is head within that head and tail within that corpus. So if we have a corpus that entirely is non-linkable, so if we have no frequency bias of anything in the corpus, then I would rather say that basically the whole corpus is a long tail corpus in a sense. Of course, measures such as ambiguity and variance might be also relevant to within that tail then distinguish specific harder or easier cases.
That's a kind of surprising answer. I would expect that entities would follow Zippy distribution, more or less the way the words do. And I wonder if maybe you're finding that this, and so I would actually, obviously it depends on where you draw the line. But I would generally expect that, recount and fewer things to get of the corpus, and sounds like you're saying no. And I wonder if that's because of annotation state.
Right. So I think for most of the datasets that we deal with, I would expect something. I would expect cases where indeed we have most of the information being in the so basically being in the tail and small. Sorry, most of the information being in the head and part being in the tail. I think so that would go for, I think, most mainstream and general information. I think once we look into cases that are very domain specific, then presumably within that domain, some things are again more head than the others. So I think then we could again look into cases and say, okay, within that domain, some things belong to the head and the rest to the tail. I think when we look into into measuring the head and the tail in domain cases, probably we need to rethink the choice of let's say a knowledge base that we deal with. So I think if we look into a sex trafficking domain, then I don't think it makes sense to use Wikidata or DBpedia as a proxy to measure the head and the tail. That's for something like PageRank, of course. And then when it comes to the other metrics, such as ambiguity and frequency, Then I agree with you that I think when it comes to frequency, I would agree with you that I think this is what we consistently shown, and I don't have this here in this presentation. But I think what we consistently have seen is that the frequency of both forms and instances is roughly Zipfian. And I would expect on that level to also observe that for domain corpora, but.
I think we have a question from Marjorie. Yeah.
Yeah, so this is Marjorie, remote from the Boston office. So I think it looks like most of how you're thinking of head versus tail is still in the direction of linking towards the external knowledge base. I think one of the most interesting things about the tail is that they're typically nils. They're entities about which you know nothing. And have you divided the tail that you've looked at into those parts?
Right. Well, thank you for your question. So I think in the analysis that we did so far, and I would say conceptually for the systems that we deal with, I would consider the nil cases to be altogether part of the tail. Of course, so this is not necessarily a static thing. So we know that there are stuff like emerging entities. So nil entities might become represented in a knowledge base, and perhaps very soon they might become head entities in terms if they become extremely important for the general interest. But I in general, I think for nil entities, I would assume that these can be seen as long tail entities because they were not interesting enough for the general population. Let's say if we take Wikipedia as a proxy, what ends up in Wikipedia is a certain measure of what we as a community, as a population find interesting. So I would say that the reason that basically having nil entities not being represented there is a choice, and it shows that those are well, infrequent in communication as well, I would say. Okay. Thanks.
So I was a little confused about the distinction between head and tail in the sense that you had like 4 measures to quantify the head versus tail, right?
Right.
Which had popularity of instance as well as the frequency of occurrence. So is this? I mean, these properties are always correlated. Could there also be frequent in text, but little information or otherwise?
Right. So, so I'll answer this question and then I'll go on to the second part just for the sake of time. But so I think again, this is a part that I didn't cover in these slides. The second half of the analysis we did in that paper was focused on correlations between all of these properties with each other. So actually, the short one-sentence conclusion is that there was more or less a linear correlation between. So the more frequent something is, the more on average, we tend to assign it different instances, and the more an instance is, let's say, found in text, the more we are starting to give it different forms, different names, and so on. Okay, so I'll go to the second part, which basically relates. So I think based on these findings, we can see that systems have certain bias towards cases that are more frequent, towards cases that are less ambiguous, and so on. Essentially, not all entities are the same. So what I'm proposing in the second half is to look into ways to build systems that can deal with such cases. And I think the way in which we can do this is through building knowledge-intensive systems. Essentially, systems that have certain intrinsic components that tells them when they don't know something. And okay. So, okay, the knowledge sounds like one of these fluffy categories, so we always talk about knowledge and context, but is there a way to actually define knowledge in some way that we can then use, is there a way to classify the knowledge so then we can actually take that as a guide and go on? Well, in the field of interpretation and framing, we have this classification from 1994, where McLachlan and Reid proposed this. They claim that people use these 4 types of knowledge when we interpret and frame text. And these types of knowledge are fairly intuitive, I would say. So the first one is the knowledge that comes from the text itself. It is the intratextual knowledge. The extratextual knowledge refers to any kind of knowledge that we have as a world knowledge, so both ontological and episodic knowledge. We have circumtextual knowledge telling us in which circumstances did this document came into existence, so who wrote it, when was it written, where, who published it, and so on. And we have intertextual knowledge that is a knowledge that comes from other relevant documents. So if we have an event that happened yesterday and perhaps there is another document giving an update today, well, we kind of need, or we might need, information from the document of yesterday to understand the one from today. So this will be the 4 types of knowledge that people use. Now, if you look at the entity linking systems, we observe that the main focus lies on the intratextual knowledge, which is the most obvious one to use, and it is very relevant. The extratextual knowledge has been used to some extent, which mostly boils down to Wikipedia links between pages and labels and so on. There is a lot of knowledge that is, I think, unexploited there that we could look into using. And the circumtextual knowledge and the intertextual have typically been left out of systems that we have. Okay, so the reason why I'm telling this is that I think we can use this within a broader framework. And the framework that I'm proposing is essentially, I call these active reading machines. So we have machines that read, and they have certain intrinsic mechanisms to tell them when they know that they don't know something. So these components would have essentially these machines would have 2 components within them. So the first one would be certain triggers, certain detection mechanism to tell them when they actually lack the knowledge or something is anomalous, and to tell them to actually go into a slower mode of reading. And in the second part, we have these strategies. So once we have detected this hunger for knowledge, we now want to go out in the world and acquire what we were missing as knowledge. And okay, these ideas have been around in all kinds of fields. For example, the idea I think it resembles a bit, for the ones that know this Daniel Kahneman book of Thinking Fast and Slow. So we have, I think, it would. What I'm intending to propose here is that we have systems that typically read fast, so we have certain default way of reading, but then we have certain intrinsic mechanisms to decide when something is not right. So we have certain ways to decide that something is. We have either too little knowledge or it's anomalous. And then when we detect those cases, then we go into slower reading and more focused and effortful reading. Okay, so I'll go a bit more into depth in these 2. So when it comes to this first category of triggers, we can look into a few things. So we can look into cases where we have very little episodic knowledge. We consult the knowledge base, and we have insufficient. So we have perhaps a representation, or we don't have a representation. Well, if we have it, the knowledge is insufficient for some downstream task. We have unresolved ambiguity, so we have still candidates that we want to choose from, but we do not have a good explanation why could we choose one or the other. And finally, we could look into anomalies detection, so we have some way to decide that, perhaps like in the case of the president, so we have certain way to have expectations about how the world works, and then we have anomalies that pop up once this extraction doesn't fit the expectations that we had before. Okay, so how do we extract the knowledge that we would be missing? Well, we could look into instantiating essentially instances of all of these specific knowledge types of all of the 4 knowledge types that I talked about before. So we can look into, well, deeper reading. I think we probably have that technology in place to a large extent. So we could look into ways to extract information from text in all kind of ways. We could look into extra-textual knowledge and try to build background knowledge models. I'll get into that in a second. We could look into circumtextual knowledge and somehow incorporate information about the author, the publisher, the time, and so on. And we could look into basically retrieve other relevant documents and read them and then go back to reinterpret what we wanted to interpret before. Okay, so I will use the final part of this talk to tell you a bit about our preliminary work on building such background knowledge models, which I think are useful both for capturing anomalies. So we use this as expectations to capture anomalies, but I think they also could be used to fill gaps in information that we extract. Okay, so this is the work that we did at Hovey in the past, and it refers to what we called the task of profiling, and the machines that we built, we call them the profiling machine. So this work is unpublished by now, so it's preliminary work. And to give you a taste of what we try to do, we try to capture such skills of people. So we try to capture skill where we have a person, so we don't know who this is, but we know that this person is an army general based in London. Well, what could you now, if I ask you to guess the nationality of this, what would it be? Okay, so we go for British, right? So fine. So that's kind of let's say an easy one. So then we go for the next one. So we have the same person. What was the gender of this thing? Probably male, right? But so there is this thing that people do a lot, and I think the potentially problematic word is stereotyping, and here we called it profiling. But I think such a task is very relevant for computers, because actually we need to build machines that can have certain expectations that resemble what actually people have. Yes.
But doesn't that risk perpetuating stereotypes? I mean, for example, the whole issue of fair AI, for example, to reduce correlations between stereotypical words associated, say, with males and the he/she line in word embedding.
Right. I think there is. I think there are two reasons why I think this is a good idea. So one is, I think having such stereotypes but being explicit about them is a good thing. So if we can actually, so I'll go later in the architectures that we built, but I think, so in those architectures we can see the predictions that machines make, and not as embeddings, but rather as clean-cut probability distributions. So I think that's one, that even though we are stereotyping, I think what we get is an explicit way to do so, because I think machines are stereotyping anyways before. But I think perhaps the more important reason within the field of information, when we want to extract information, is that such expectations are used by people, and given that these texts were written for people to read within certain circumstances and with certain expectations, I think we need such expectations to be also built in machines in order to understand it, because otherwise it's very hard to, for instance, make a distinction between saying, I don't know, he's a French but he doesn't like wine, against he's an athlete but he doesn't like wine. So we have this situation where we essentially use kind of same formulation, but for people they mean very different things.
So while it might be useful for maybe interpreting text, maybe the broader goal of such NLP, such text analysis, would be perhaps to make decisions. So if you're using certain heuristics, perhaps, or stereotypes, which might help you with analysis text, it could be that you're making decisions that are also stereotyping and maybe biased against the minority or against, say, women, you know.
Right. So I think that would boil more to the first point that I mentioned. So I think it's it's a skill that it's a mechanism that people use when we read text, and I think it's at least good to have it as a formal way to generate expectations. And
maybe in some sense that's true, but I'm just saying specifically inferring demographics from words that are not necessarily demographic related. Like mother obviously might be related to woman, but doctor, to associate doctor, say with white male, might be, or male might be creating a certain stereotype that is not beneficial to the AI.
Right. So I think, and I'll go on after this, but I think I think this is a territory that I think is worth investigating, and I think as part of the experiments we also tried to combine this to compare this against human expectations and see how this relates to that. There are findings in social psychology saying that many of the stereotypes actually have correlation to what we find in instance data. So there are things to be. So I think there is value in that, but I do agree that there is caution that should be taken into account there. Okay. So this is just to show that that we have that this kind of expectations could change with additional evidence. So if we have the same case, Army General based in London, but now if you know that that person received such an award that is typically awarded to females, the expectation of gender probably would change to that. Okay. So social psychology tells us that this kind of stereotypes, profiles are actually used by people as shortcuts to thinking. So we use this in order to make fast and efficient decisions when there is absence of more explicit information. And why do we need this for long tail entities? Because we actually have a lot of gaps. So we have a lot of information that is not specified based on. So paraphrasing pragmatic principles, this basically means that if something is not given, we can typically assume that it's either as expected or it's not relevant within the given context where we deal with it. Okay, so how did we do this in practice? Well, the task is essentially given k feature values that we know about a certain a certain entity. We want to predict expectation for the remaining n minus k. So if we know that the occupation is Army General and we know that the birthplace is London, we want to predict everything else that we don't know. And it can be any subset of things that we know, and we always predict expectations or probability distributions for all the other properties. Okay, so the approach will be having a typical knowledge base to use some kind of neural networks or basically some methods to generalize over this. We use neural networks, but it doesn't really need to be the case. And then once we have these generalized models that give us expectations based on incomplete knowledge, we can apply profiling models to these profiling models to a downstream task. And one of the tasks that we tested this on is nil clustering. So we have two representations of a nil entity, let's say in two different documents that share the same surface form. And we have incomplete information in both of them. Well, how do you actually get to compare this? We try to use this kind of profiling to kind of normalize the representations. Okay, so this is just to give you a flavor of what we did. So indeed, we looked mostly into demographic properties. We took Wikidata, 3 million people at that time. We used 14 properties. The data is very sparse. So then we used this data and we threw that in these two approaches. In the first one, we have essentially, this is my last slide, by the way, before the conclusion. So in the first case, we have this incomplete set of known attributes. So we learn their embeddings in the input layer. It essentially goes connected through a single hidden layer, and finally we predict the probabilities for all n variables. So we use certain tricks to deal with sparsity, such as we used masking of inputs, and we used dropout on the input layer here to make the network a bit more robust and being able to learn a bit more dependencies between the inputs. And the second architecture is essentially the same in the middle layer and in the output, but in the input there we try to experiment with providing this architecture with an entity embedding and then making a prediction. Okay, so just to conclude,
You don't have results?
sorry, I do have results, but I left them because of lack of time. And if there are a few more minutes, I would go back to.
You have a few minutes.
A few minutes, okay.
Yeah.
Okay,
So
I'll go back to that.
It's intriguing to see the results.
Okay, great. Okay, fine. So we have we use two baselines in all of these experiments: most frequent value and naive Bayes classifier. We did three kinds of experiments. So the first one is where we okay. So the problem with evaluating such an approach is that there is no good benchmarking data to actually measure this on. So we tried to find a way around this, and we essentially looked into three ways to evaluate it. So in the first case, we compared this to Wikidata, which essentially is knowledge-based completion itself. So we just took the top one value that our system predicted, and we checked how often does this correspond to actual cases in Wikidata. In the second case, we compared this to human judgments through a crowd sourcing task. And finally, we looked into clustering of nil entities in text. Okay, so in comparison to Wikidata, we looked at all 14 properties, and the first two cases here, the first two columns correspond to the two baselines that we use. So we have the most frequent baseline and the naive Bayes baseline, and the other two columns relate to the autoencoder. So that's our first architecture, and the other one, the fourth column, refers to the embedding-based predictor, which is the architecture that uses entity embedding as input. So what you can see here is that okay, so overall most of the bolded cases are in the last two columns. So okay, the autoencoder and the embedding-based predictor are in general better than the baselines. I think there are two interesting observations in this table. So one is that per property we see quite a big difference between the two architectures that we built. So I think this says that in some cases it makes more sense to give to start with this entity embedding, which has more information but also more noise. So the system here probably captures for these properties some information that's more or less explicitly given in text or very easy to extract. Whereas for others, it just makes more sense to give the system a clean cut, but a smaller set of given properties, and that's the cases where the autoencoder works better. I think what is also interesting is that if we compare now these results with the entropy, we see that in cases where we have very low entropy, like sex or gender, or century of birth, or lifespan range, in these cases, the baselines perform quite well. So in these cases, when we have low entropy, using a naive Bayes or using a most frequent baseline even doesn't perform much worse than our systems. But in cases where the entropy is very high, so we have something like an educated ad, then we need perhaps a more sophisticated neural network-like system to learn these dependencies and improve over the baselines more.
Can you stay in that table 1 second?
Yes.
So, so native language and century of birth have some similar entropy, and the autoencoder does similarly, but embedding does terrible. Native language.
Right, native language. Okay, so I think there is something specific to the property of native language. So this is something this has to do with the fact how Wikidata has encoded this property, which is So it is missing common sense knowledge by itself. So whenever somebody is an American citizen, but his native language is English, that information is very often not extracted. So what is very often the case with native language specifically is that this property mostly encodes unusual cases. So this is probably not the best property in this shape to stereotype on.
What's the last column?
Sorry? Oh, the rest column. So that's the entropy, the normalized entropy for this property. Okay. So we also did human evaluation, which was not as satisfactory, I would say, for the reason that the agreement that we got between the annotators was fairly low, which which might mean that the properties or the way we provided this to the crowds were not provided in the right way, but it also might mean that some of the
How did you create human evaluation? Was this mechanical Turk or was this the expert domain?
So we used figure 8, which is the former Crowdflower. Like mechanical Turk, so from the same range. Okay, so I'll go on. Okay, so I'll just comment on this briefly. So we have this evaluation on the human against human judgments. Here we compared distributions using Jensen-Shannon divergence between the human judgments and the system. So here you can see that the improvement of the autoencoder is not much. So lower divergence means better results, but you can see that the results are fairly comparable, especially with the naive baseline. So this is something that is that I think we should just look further into and see what this actually means. In the final experiment, what we tried to do is what I described a bit earlier. So we have two documents. We first run certain attribute extraction over these two documents for entities that are mentioned there. And then, given a case where the entity shares the surface form in these two documents, then we want to cluster these cases. How do we do that? We essentially enrich this local context, local representation of this entity with these probability distributions that we get from the profiling, and then we run a certain similarity metric to see whether this actually improved something, whether it managed to normalize things for us and let us either pull apart or essentially bring closer to representations that we could not perhaps compare otherwise. Okay, and we did this on the data that I mentioned earlier from the gun violence domain, long-tail entities and events. When it comes to the entity ambiguity here, we also did certain tricks to increase the ambiguity artificially. So apart from the original data, we also looked into cases where we had everybody having the same name, same surname, or same name entirely to just see what is the behavior once the ambiguity kind of explodes. And these are the results. So you can see that. So I'll explain briefly. So what we get here is we used two reasoners. So these reasoners are essentially what I called earlier the similarity metric. So once we have certain representation of two cases, being it the one we extract or being it the one enriched, we want to now somehow be able to say whether these two things are the same. So these are two reasoners that we used. In the exact one, we only say that the two things are the same if all the properties are exactly the same. And in the no clash, it's basically two things are the same as long as there are no clashing property values that we get. And you can see here that for the exact reasoner, if we apply more and more of the profiler, so the tau means the tau is a confidence threshold. So the more we add of this profiler, the more it actually helps normalize values and essentially establish this identity. And when it comes to the no clash reasoner, here it helps to use a profiler to some extent. Then essentially we start over stereotyping and starting to get into clashes that eventually decrease performance. Right. So I have certain discussion on this, but I also know that I'm over time.
You still have 1 minute.
1 minute, okay.
I think we have. I think you may be able to have the discussion questions on the one-on-one. And
yes.
maybe we have time for one last question. Somebody wants to ask a last one?
Yes, please.
I was just curious to know, like when you deal with that long tail, how does it relate with like slang vocabulary? If we think about like some of those sexual acts or human trafficking, they're probably using like quite a different language compared to the language we.
Right. Yeah. So I think your question is on right on point. So in this analysis, what we looked into is news documents. So this analysis is specifically targeted on the newswire. I think that in order to apply this to other domains, being it Twitter data, slang, I don't know, other domains where people in illicit domains, I think we might need to take other things into account as well. For example, misspellings and deliberate obfuscation of content and so on.
Well, let's thank Philip for an excellent talk. Thank you. So Philip will be here this afternoon. Tomorrow morning, he's going to be on campus and is returning in the afternoon to talk to some folks. So if there are anyone who's not on the schedule who really would like a slot with Philip tomorrow, we can ask him to stay a little bit later and fit you in. So let me know if you want to talk to him and you're not already on the schedule.
Okay. Thank you guys for your attention.
Thank you.